Hi, in this video I want to give a supplementary perspective to Pishro-Nik's Chapter 10, Introduction to Random Processes. Now, you can also get another perspective from this video series by Jules Peterson. He covers pretty much the same material, and it's quite clear, so I recommend this as well. So I'm just going to give a 10,000 foot summary of the concepts, kind of trying to get the big picture. All right, so section 10.1.0, it's actually called Basic Concepts. Okay, so I can summarize the idea of stochastic processes by saying that stochastic processes are the mathematical representation of time. Now, I said stochastic process here, I said random process here, same thing. So what do I mean that stochastic processes are the mathematical representation of time? So we think of time as a series of moments, and at each moment quantities have value: position, velocity, temperature, and so on. These values are different at different moments, and the values are correlated. Right? My position now is close to my position in 1 second. So that can be expressed as a correlation. So these correlations express that time includes both deterministic and predictable changes and probabilistic random changes. All right, two aspects. There are some changes we know, some changes we don't know. And random we have modeled as random variables. So these random changes may in fact be due to factors we have no information about. So what we call random sometimes just reflects a lack of information. All right, it means that we don't have a formula for exactly what the change is, so we just include multiple possibilities, and that's modeled as a random variable. Okay. Now, the series of moments can be discrete or continuous, and a continuous series can always be approximated as a discrete series. Right? So we can think of time as moment by moment, second by second, or we can think of it as a continuous scale. When computers are used to simulate stochastic processes, first the process must be discretized. So in practice, whenever you compute or model stochastic processes, they are discretized. But we still use the continuous theory. It's very useful because it expresses the fact that when you make a small change in time, then there's a small change in the random variable. Okay, so continuous theory is still very important, even though in the end the stochastic process is implemented on the computer as a discrete process. Okay, all right. So here's the formal definition given in the chapter. Continuous time random process. I said stochastic process. Again, it's the same thing. It's a random process. So here we have a random variable as a function of time, and time is in a set. So this set could be a continuous set. So the only difference between continuous and discrete is the nature of this set J. Right? So we have continuous or discrete sets. So the two types of processes really can be considered under the same rubric. Okay. Now, here we're thinking of a random process as a series of random variables. Now, alternatively, you can consider the entire sequence of values as a multidimensional random variable. We talked about vector random variables before. So I could take all of these random variables. In fact, there's a continuous infinity of random variables here. And I could think of that as a continuously infinite random variable. Okay, that kind of blows your mind as a concept, but you can think of it that way. So each possible sequence of values is called a sample path. Okay, so one sample path would be an infinite dimensional vector, if you will, that represents the entire behavior of the system over all times. Okay, so sometimes we might use that perspective. Okay, so when we're talking about random variables, of course we express random variables in terms of PDFs and CDFs. And since this stochastic process really consists of a series of random variables, we can think of the joint density and the joint CDF between the random variables at different instants. Now, in the real world, often randomness comes from Gaussian distributions. So in many cases, these are joint Gaussian distributions. So this is one of the reasons why joint Gaussians are studied, extensively studied, and they covered in the earlier chapter, because they do pop up quite a bit in stochastic processes. Okay. And the nice properties of Gaussians carry over to nice properties of stochastic processes. Okay. And we'll get more into that in later chapters. Right. So, of course, when we talk about random variables, we talk about means, covariances, and correlations. Okay. So let's apply that to the case of a stochastic process or random process. So since these x of t are a series of random variables, by taking their means, you produce a series of numbers, which we can think of as a function of time. Right? For each time t, you can take the mean of this random variable. Okay? So this produces a function called the mean function, which is a function of time. Now, of course, if your time is discrete, then this will be a function of discrete instance. Okay? We can also consider the correlation between two different instances by using the joint density. We can use the joint density to compute correlation. And as I said, in the case of Gaussian, we can use the Gaussian correlation formula. Okay. So two common concepts are the autocorrelation, which is the correlation between the random process at two instants, okay, denoted by Rx, and we also have covariance, which is just the centered version of the correlation. Now, important special case of the autocorrelation is when T1 equals T2, and then you simply get the mean square of x at that time, and the covariance function becomes the variance of x at that time. Right? Okay. Now, because of the symmetry of covariance, it's always true that Rx of T1 T2 equals Rx of T2 T1. So you have symmetry there. Okay. Now, typically, if you think about a phenomena, typically the correlation and covariance will decrease as the time increases. Like, for instance, if you think about distance or you think about some random motion, then the longer you wait, the farther away the object will move, so the correlation will decrease. Okay, so typically that's what happens, and we'll see examples of that later. Sometimes the correlation depends only on the difference in time. Okay, then we can express autocorrelation and autocovariance as functions of one variable, which is just the difference. And we'll talk about this important special case later. All right, multiple random processes. Okay, so we've talked about multiple random variables. Now we talk about multiple random processes. So consider the relation between two random processes. Each random process can be considered as a collection of random variables. As we saw, at different instants, we have different random variables. Okay. So we can consider correlations and covariances between two different instants for two different random processes. So this is simply a generalization of autocorrelation and autocovariance. So we talk about cross-correlation and cross-covariance, which is the analogous concept when you're talking about two different random processes. Okay. All right. We can also talk about independence of random processes by requiring that the x's at all instants are independent of the y's at all instants. So remember that independence means that the joint densities and CDFs are products. If I have the joint density, for instance, if x of t1 is independent of y of t1 prime, that means that the joint density of x of t1 and y of t1 prime is a product of the density of x and the density of y. So typically that's very difficult to determine. When you make a measurement, you typically don't measure an entire distribution. So theoretically this is important, but practically this is very difficult to determine. Okay. Intuitively, you can know when two processes are independent. Like you talk about the price of eggs in Japan and the temperature in New Hampshire. Those should be independent because you would think that the factors that affect the price of eggs in Japan really have nothing to do with the factors that affect the temperature in New Hampshire. Okay, so stationary processes. So how does the overall situation change over time? All right, we're doing mathematical modeling. Typically, we want to model a realistic situation. So this is the big question. How we are trying to figure out how situations or systems change over time. Now, often that involves prediction. If you want to predict something, you need the past to give you some information about the future. All right? If the system is going to behave completely differently in the future, then how can you predict it? But if you have a process that's stationary, then the random properties of the observed quantity x of t do not depend on when you start observing it. So, for instance, over the short term, we would expect the random behavior of a stock market. You have random fluctuations, and the random fluctuations today, in some sense, resemble the random fluctuations tomorrow, unless you have a stock crash or something else like that. Same thing with temperature. You have temperature fluctuations. You would think that the temperature fluctuations over a short time would not change very much. So temperature fluctuations during 1 hour may be a good model for temperature fluctuations during the next hour. Now, there are two common notions of stationarity. There's strict sense stationarity, like independence, looks at joint densities. And this means that you can shift the time scale without changing the joint density. So if I make my measurements today, or I make my measurements tomorrow, I would expect similar autocorrelations, autocovariances, and similar joint densities. So that's what this is saying. If I take a set of random variables associated with different times and consider the joint density of those random variables, that's going to have the same joint density as this set of random variables, where delta is arbitrary. So I can shift the times arbitrarily and expect the same density, same distribution. Okay. And as I said before, determining distributions is quite difficult. So typically in practice, instead of requiring strict sense stationarity, we require wide sense stationarity. In this case, we just look at the correlation functions instead of the joint densities or distributions. Okay, so if the correlation function does not change if time is shifted by any delta, that means the correlation function only depends on the difference between times. So this is the situation that I mentioned above here, that if you have a stationary random process, the correlation depends only on the absolute time difference. Right? So that's called wide sense stationary. So that's what he says here, that the covariance is different. And so he also requires that the mean function is a constant function. Okay. If the mean is not constant, then the joint densities cannot be the same. But sometimes if you have a random process where the mean is not constant, you can subtract out the mean and get a stationary process. That's actually a common strategy. Okay. This is continuous random process, discrete random process. Notice the only difference is that he's replaced the continuous time variable with a discrete time variable. Okay. All right, now during this section, he introduces other concepts: expected power, joint wide sense stationary, cyclostationary derivatives, and integrals of stochastic processes. So what he calls power is the autocovariance when T1 equals T2. It turns out that's the expected value of x squared at that common time. So now you can think of the random variable at that time as random jiggling. So let's replace that random jiggling with something that's oscillating, that's moving back and forth. Now, if you remember from your physics class, energy is proportional to velocity squared. So if you have an oscillator, the average kinetic energy is proportional to the average velocity squared. So here's the equation of an oscillator moving sinusoidally. A is the amplitude, omega is the angular frequency, and the kinetic energy is proportional to the velocity squared. If you take the derivative, you're going to get the omega A cosine omega t squared. Right? You pull down the omega when you do that. Now this in turn is proportional to the amplitude squared. Okay? And the variance is the average of the squared amplitude. All right. In fact, when you average the cosine, you'll get 1/2. You can think about why that is. It's due to the fact that cos squared plus sine squared equals 1. But the variance is proportional to the squared amplitude, and here the energy is also proportional to the squared amplitude. So it makes sense to identify energy with variance, and the variance, as I said, is the auto covariance, to the autocorrelation when T1 equals T2. So that's why it's called energy. This actually comes up all the time in signal processing. Okay. All right, so the next section is Gaussian random processes. And in the real world, a lot of randomness is Gaussian. In signal processing, you always use Gaussian noise. So it's often the case that random variables xt are jointly Gaussian. So one random process can be thought of as a whole bunch of jointly Gaussian random variables. So in this case, the random process itself can be seen as an infinitely dimensional Gaussian random variable. Now, there are more technical details here. He makes more definitions. Go ahead and read the chapter, and that will enable you to do the calculations necessary for the homework. All right, thanks for watching.